A game-changing move that does not come from OpenAI, Google, or Meta.
There is a new model that has all of the valley buzzing.
But from a Chinese lab called DeepSeek.
25 may go down in history as DeepSeek Day.
DeepSeek shaking up global tech.
NVIDIA losing nearly $600 billion in market cap today alone.
With such a mindset, DeepSeek may force AI innovation forward, and China could be at the forefront of the global AI race.
The DeepSeek rabbit hole just keeps getting deeper and deeper.
But in the last few days, a model called DeepSeek has come out, and a new model called DeepSeek R1 that are very...
DeepSeek has taken over ChatGPT's job. I'd say some of it, not all of it. With its server being busy several times a day, I find myself going back to good old reliable ChatGPT. Feeling like going back to your main car after flirting with your flashy sidecar with new tires. Anyway, I'm sure you've heard of the basics on DeepSeek. How it has turned America, Wall Street panicking, hence the fall in AI-based tech stocks, losing billions in a day, yada yada. But I've had a hard time trying to understand how DeepSeek inherently works through videos and most material out there. So I went directly to the source, the DeepSeek documentation. I mean, I hate writing documentations, but they sure do come in handy when you need them. Yeah, it's about to get technical.
Well, the introduction in DeepSeek's documentation has everything you need to understand most of its functionality. It emphasizes the importance of post-training in the full training pipeline. What is the full training pipeline, you may ask? So it involves several steps and I'll highlight them. Number one, it's problem definition. Here's whereby you define the problems that you want to solve and identify the objectives and constraints. Then you have the data collection. Normally 3 steps. You clean the data, normalize and standardize the data. Then you can perform some feature engineering to create relevant features. Next, we have data splitting. Here you just divide it into training, validation, and testing dataset. Then you have the training, whereby you train the model from the training dataset, and you use techniques such as cross-validation to ensure robustness. Then there's the validation, where you tune your hyperparameters using the validation set, and you perform model selection based on validation performance. Then now we come into the post-training, whereby there is model evaluation. Here you evaluate the model on the test set to assess its performance. There is the error analysis, where you analyze errors to understand the model's weaknesses. There's model interpretation, where you use techniques such as SHARP or LIME to interpret the model decisions. There is model optimization, where you optimize the model, and A/B testing, where you compare the model against existing solutions in a controlled environment. And then next, there will be the deployment into a production environment, and then you monitor and maintain the model. So the importance of this training pipeline is that, number one, it enhances the accuracy on the reasoning tasks. So the model will be able to generalize well to unseen data through metrics such as the accuracy, F1 score, recall, and precision. And then it's going to identify the specific cases where the model fails. Secondly, it's going to align with the social values, whereby stakeholders will be able to understand how the model makes the decisions. Then it's going to adapt to user preferences. And finally, there will be minimal computational resources used against the pre-training. So it reduces the model size and computational requirements and makes the model more efficient for deployment, especially in resource-constrained environments. For example, maybe in your Raspberry Pis or in mobile devices, edge computing, for example, the IoT devices and smart home devices, in autonomous vehicles such as cars and drones, healthcare devices, your smartwatches, in real-time gaming through the consoles and VR and AR headsets, and also retail and customer service. So you can see all those resource-constrained environments require minimal computational resources. And on a side note, I'll explain the sharp and lime. They are basically used to interpret and explain the predictions of machine learning models. So both sharp and lime aim to make complex models more transparent and understandable by providing insights into how the model makes decisions. So sharp in full is shapely additive explanations, and it's based on the shapely values, a concept from cooperative game theory. You can do more research on that. So it provides a unified measure of feature importance by fairly distributing the contribution of each feature to the prediction. So its use cases are explaining the individual predictions in complex models like deep neural networks or ensemble methods, and understanding feature importance and interactions in the model. Well, now to lime, local interpretable model agnostic explanations. It focuses on explaining individual predictions by approximating the complex model locally with an interpretable model. For example, you can compare how ridge regression works in comparison to linear regression. Its key concepts are local approximation, whereby it creates a simple model that approximates the behavior of the complex model in the vicinity of a specific instance, and it's model agnostic, meaning that it can be applied to any machine learning model regardless of its complexity. So the use cases are explaining individual predictions in black box models, debugging and validating model behavior for specific instances. Its creators highlight that OpenAI's O1 introduced this, whereby it increases the length of chain of thought reasoning process, which leads to improvement in reasoning tasks. This approach involves dynamically scaling the length or complexity of the reasoning process during inference, allowing the model to adapt its problem-solving strategy based on the difficulty of the task. So it generates more intermediate steps for harder problems and reduces them for simpler ones. Chain of thought reasoning is a technique where a language model generates intermediate reasoning steps, like a thought process, before arriving at the final answer. So for example, if we have a problem, if John has 5 apples and gives 2 to Mary, how many apples does he have left? In chain of thought reasoning, first we start with John has 5 apples, then he gives 2 to Mary. So he now has 5 minus 2, which is 3 apples, and the final answer is 3 apples. So there have been challenges on effective time test scaling, and there have been some approaches to solve it. For example, process-based reward models, reinforcement learning models, and search algorithms such as the Monte Carlo tree search and the beam search. But none has achieved general reasoning performance like OpenAI's. Now comes DeepSeek, which uses pure reinforcement learning to improve its reasoning capabilities. It used pure RL to get DeepSeek R1-Zero. It aims to develop reasoning capabilities without supervised data, focusing on self-evolution via pure reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns to make decisions by performing actions in an environment to maximize some notion of cumulative reward. The agent learns from the consequences of its actions rather than from being explicitly taught, and it aims to find a policy that dictates the best action to take in each state to achieve the highest reward over time. So it has been used in games, robotics, recommendation systems, autonomous vehicles, and healthcare. The key components of reinforcement learning include an agent, who is the learner or decision maker, the environment, which is the world through which the agent moves, including everything that the agent interacts with, state, a representation of the current situation of the environment, action, a set of possible moves the agent can make, reward, which is the feedback from the environment in response to the agent's actions, which the agent aims to maximize over time, the policy, which is a strategy that the agent employs to determine the next action based on the current state, the value function, a function that estimates the expected cumulative reward from a given state following a particular policy, and the Q value, which is a function that estimates the expected cumulative reward for taking a particular action in a particular state and then following the policy thereafter. So there are two types of reinforcement learning, which is model-based and model-free. Model-based, the agent builds a model of the environment and uses it to plan actions. Model-free, the agent learns directly from interactions with the environment without building a model, and the common algorithms include Q-learning and SARS. So DeepSeek uses the model-free reinforcement learning because it focuses on learning through trial and error, guided by rewards, rather than relying on a pre-built model of the environment. The algorithms used in reinforcement learning include Q-learning. It is an off-policy algorithm that learns the value of actions in particular states. There are deep Q networks, which combine Q-learning with deep neural networks to handle high-dimensional state spaces. We have the policy gradient methods, which directly optimize the policy by adjusting the parameters in the direction that increases expected reward. And finally, actor-critic methods, which combine value function approximation and policy gradient methods using both an actor and a critique. The actor being a policy and a critique being a value function. So DeepSeek leverages policy gradient methods as they are well suited for tasks where action space is continuous or high dimensional, making them ideal for complex reasoning tasks like those tackled by it. Now we have the DeepSeek's pure reinforcement learning process. It uses DeepSeek V3 base as the base model and GRPO as the reinforcement learning framework. GRPO is the generalized reinforcement learning with policy optimization. It uses policy gradient methods to directly optimize the policy. It allows self-evolution through pure reinforcement learning. It employs rejection sampling to filter high-quality outputs from the reinforcement learning checkpoints, and it supports a multi-stage training pipeline where the model undergoes iterative refinement. After thousands of reinforcement learning steps, DeepSeek finally got DeepSeek R1-Zero, and it got an 86.7% accuracy on the AIME 2024 test, which rivals OpenAI's 010912. AIME stands for Automated Interpretable Machine Learning. It is a framework or approach aimed at making machine learning models more interpretable and understandable by automating the process of generating explanations for model predictions. Its goal is to bridge the gap between complex machine learning models and human understandable insights, ensuring that stakeholders can trust and effectively use these models. So the two challenges, among others, that R1-Zero faces include poor readability and language mixing. DeepSeek R1 first requires some cold start data to fine-tune DeepSeek V3 base. Cold start data is the initial data, or lack thereof, when deploying a system, algorithm, or model that relies on historical information to function effectively. This data can include writing, factual question answering, or self-cognition tasks. The model gains initial task-specific capabilities, preparing it for further refinement through reinforcement learning. There are three cold start problems. Number one, user cold start, which occurs when a new user joins the system and there is no historical data about their preferences or behavior. For example, a new user on a streaming service with no viewing history. There is also item cold start, which occurs when a new item is added to the system and there is no historical data about how users interact with it. For example, a new movie added to a recommendation platform with no user ratings or reviews. Number 3 is the system cold start, which occurs when a new system or model is deployed and there is no historical data to train or initialize it. For example, launching a new e-commerce platform with no prior transaction data. So how do we address these problems? Content-based filtering, whereby we use metadata or features of users or items to make initial recommendations. We have hybrid models, which combine collaborative filtering with content-based methods to leverage both user-item interactions and item features. We have transfer learning, where we use data from a related domain to initialize the model, and active learning, where we prompt users to provide initial feedback or preferences to bootstrap the system. So DeepSeek leverages the multi-stage training pipeline. The first part, as we've said, is fine-tuning DeepSeek V3 base with cold start data, and then the reasoning-oriented reinforcement learning, which helps the model evolve to DeepSeek R1-Zero, as we've talked about before. This improves the model's capacity for complex reasoning through reinforcement learning. Third, we have rejection sampling for supervised fine-tuning data. So we want to create high-quality supervised fine-tuning data that will help refine the model. So the process is that, number 1, we undergo rejection sampling, whereby during the RL process, the model generates candidate outputs. So these outputs are filtered using a quality criterion, either a reward model or human feedback. So there is a proposal distribution and a quality criterion. So the distribution is the reinforcement learning checkpoint, which we received from the previous step, which is DeepSeek R1-Zero, that acts now as the proposal distribution and it generates the candidate outputs. The quality criterion is only the outputs that meet a high quality threshold are retained for supervised fine-tuning data. And then the second thing that we do is to combine the data. So the high quality outputs from the rejection sampling are combined with supervised data from DeepSeek V3 base to create a new supervised fine-tuning dataset. And what is supervised fine-tuning data? So this is labeled datasets that are used to fine-tune pre-trained models in a supervised learning setting. So this process involves adjusting the model's parameters to improve its performance on a specific task by training it on a smaller task-specific dataset. We have the pre-trained models. These are models that have been initially trained on large general datasets, for example, BART and GPT, to learn general features or representations. So then we fine-tune this, and this is the process of further training these pre-trained models on a smaller task-specific dataset to adapt them to a particular application. So for example, you can fine-tune GPT-4 for contract review. So you get the pre-trained model, which is GPT-4, initially trained on a vast range of general text data. And now we take this supervised fine-tuning dataset, a labeled dataset containing legal contracts with annotations, including the clauses flagged for risk, obligations, and missing terms. And now we go through the fine-tuning process, whereby the model is trained on this dataset using supervised learning, adjusting its parameters to accurately identify and classify contract clauses. And then the outcome is that we have a fine-tuned model that can analyze contracts more effectively, automatically highlighting the risks and ensuring compliance in legal reviews. So the fourth step is now retraining DeepSeek V3 base. The DeepSeek V3 base model is retrained on the new supervised fine-tuning dataset, which includes both the original supervised data and the high-quality outputs from the rejection sampling. This step ensures that the model retains its general capabilities while improving its performance on reasoning tasks. The model becomes more robust and capable of handling complex reasoning tasks. And then finally, we have the additional reinforcement learning process. By now, this model is exposed to a wide range of prompts and scenarios to allow generalization well across different tasks and domains. Now, after this, we have now reached a new checkpoint, the DeepSeek R1, whose performance is on par with OpenAI O2 1217. So there are several issues that DeepSeek R1 faces. The first being prompt sensitivity. So there are two types of prompts, few-shot prompts and zero-shot prompts. In few-shot prompting, the model is provided with a few examples, input-output pairs, to guide its behavior. However, for DeepSeek R1, this approach consistently degrades performance. There are several reasons for degradation. Number one is overfitting to examples. The model may overfit to specific examples provided, leading to poor generalization on new inputs. And the next is ambiguity in examples. If the examples are not carefully chosen or ambiguous, they may mislead the model. Then we have task misalignment. The examples may not fully align with the task, causing the model to focus on irrelevant patterns. And finally, there can be increased complexity because few-shot prompts add complexity to the input, which may confuse the model or lead to suboptimal outputs. Then we have zero-shot prompting. Here, the model is given only a task description and no examples. For example, reasons it may be better are that, number one, you give it simpler input. When the input is less cluttered, it reduces the risk of confusion or misinterpretation. Then there is better generalization. The model relies on its pre-trained knowledge rather than overfitting to specific examples. Then you have given it clear instructions. When the task and output format are directly described, the model can focus on generating the desired output without being distracted by examples. The second issue it faces is general capability, whereby its capabilities fall short of DeepSeek V3 in tasks such as function calling, multi-turn, complex role-playing, and the infamous JSON outputs. Then there is language mixing, because DeepSeek R1 is currently optimized for Chinese and English, which may result language mixing issues when handling queries in other languages. And software engineering tasks, due to the long evaluation times which impact the efficiency of reinforcement learning process. So large-scale reinforcement learning hasn't been applied extensively in software engineering tasks. Based on the DeepSeek R1 paper, there hasn't been much improvement compared to DeepSeek V3 on software engineering, but they hope to improve as time goes by. So finally, there are benchmarks that have been used to test DeepSeek R1. I wanted to understand what they meant by DeepSeek R1 is better at this compared to OpenAI. Like I was just hearing what it does, but I didn't know what these tests are. So that is why I wanted to include this as part of the video. So the first is the massive multitask language understanding, which is a benchmark designed to test a model's multitask language understanding across 57 diverse subjects, ranging from STEM to humanities and professional domains such as law and medicine. So it consists of multiple choice questions that require not only factual knowledge but also reasoning and comprehension. Reminds me of SAT papers. What features does MMLU incorporate? Number one, there's broad coverage, so it tests knowledge across a wide range of disciplines. Then the difficulty, it includes questions of varying difficulty levels from advanced to basic. And zero-shot and few-shot evaluation. It is evaluated by both query forms, as I had explained earlier. So its purpose is to evaluate how well models generalize across diverse domains and handle tasks requiring both knowledge and reasoning. So the example questions can be finding derivatives in STEM. For humanities, you can find a question like who wrote the Republic and what's its main theme. And professionally, you can find what is the standard of proof required in a criminal case for a law situation. And secondly, there is MMLU Pro, whereby the Pro stands for progressive. It is an enhanced version of MMLU that focuses on progressive reasoning and deeper understanding. It includes more challenging questions that require multi-step reasoning, synthesis of information, and application of knowledge. The questions are designed to test not just factual recall, but also the ability to connect concepts across domains and solve complex problems. So the features include that it has a higher difficulty because the questions are more complex and require advanced reasoning. It is interdisciplinary, where it encourages the models to integrate knowledge from multiple domains, and it has real-world relevance, whereby the questions mimic real-world problem-solving scenarios. So it is done to push the boundaries of model capabilities by testing their ability to handle tasks that require deeper reasoning and interdisciplinary knowledge. And the questions can be, in chemistry, given the chemical properties of sodium and chlorine, explain how they combine to form table salts and why the process is exothermic. Or in computing, analyze the ethical implications of AI in healthcare, considering both patient privacy and potential for improved diagnostics. The third test is the GPQA Diamond, by the General Purpose Question Answering Diamond. It is a highly challenging benchmark designed to evaluate models on expert-level reasoning and knowledge. So it focuses on questions that are difficult even for human experts, requiring deep domain expertise and sophisticated reasoning. So this benchmark is designed to test the upper limits of model capabilities, particularly in STEM and technical domains. So its features include the expert level questions, whereby the questions are curated to be challenging for domain experts, the depth of knowledge, whereby it requires not only the surface level understanding, but also the ability to apply the knowledge in novel ways, and high precision, whereby it emphasizes the accuracy and reliability of answers, as even small errors can lead to incorrect conclusion. It is used to assess whether models can achieve expert-level performance in specialized domain and handle questions that require deep, nuanced understanding. So for example, questions such as explain the mechanism by which the CRISPR-Cas9 enables gene editing, including the role of guide RNA and the PAM sequence. Oh god, this is ribonucleic acid, at least I remember. I don't know what PAM is. And you can find another question like derive the equations of motion for a double pendulum system and analyze its chaotic behavior under small perturbations. This has been a longer video than I expected, but I sure hope that you've understood the technical background of DeepSeek and you can do more research to understand some of these machine learning and deep learning concepts will come to power with how these things work. Yeah, so have a great day. Remember to subscribe and like.